Hi, Math 30-1s. Starting into the last chapter for the Math 30-1 course for you, we're going to be studying and taking a look at something called permutations and combinations. So basically, this is the number of ways that things can be ordered or the number of ways that things can occur. So just to start today, we're going to talk about something called the fundamental counting principle. Okay, so what happens with this is that basically we take a look at all the numbers or the stages or parts of something that is happening and determine the number of ways things can happen at each stage or step of the process, and then we multiply those values together to get the total number of ways that something can be created or made or occur. All right, so just starting at the top, it says in this unit we will solve problems involving the application of what we do call the fundamental counting principle, permutations, which will have restrictions and repetitions, and also combinations. We'll also explore patterns in the expanded form of x plus y to the n, which is just we take a look at patterns that occur when we expand binomials, and solve problems using what we call the binomial theorem. So to start, it says Joe is shopping for a car. The dealer says that he has 3 different models and that each model is available in 5 different colors. Use the tree diagram to determine how many different choices Joe has. Okay, so when you take a look at that, you can see that he does have 3 choices for the models, model 1, model 2, and model 3. And then for each model, there are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 colors for each model. Okay, and that results in all of these final different cars, okay, that he can potentially buy. So when I add up all those check marks there, okay, you will see in total here, there are 15. So that's the answer to A. He has 15 different models to choose from. It says, look at the number of choices there are for the model and the number of choices there are for the color. How do you use these numbers to arrive at A? Well, that's kind of what I was talking about. You can think about step 1 as the choice of model, and you can think of step 2 as the color choice that he has, right? Or, you know, whatever level of whatever we're building. But he has 2 choices to make. 1 for model. There are 3 options there. And then he has 5 choices to make for color. We multiply those to get that total of 15. Okay, so remember in math that when we're talking about calculating, when I say the word and, whether to myself or out loud, that means we are going to be multiplying. So he has 3 choices for the model, and then he has to choose the color for which there are 5 choices. Okay, so you're going to be talking to yourself a lot in your head when you do these questions. And just remember, if you're saying and, we want to multiply. If you're going to say or, then you will be adding, okay? And means multiply, or means add. So the fundamental counting principle looks like this. Consider a task made up of several stages. If the number of choices for the first stage is A, the number of choices for the second stage is B, and the number of choices for the third stage is C, then the number of the ways the task will be completed is A times B times C. Okay, and this is called the fundamental counting principle. So again, how many steps or stages are there in the process? Multiply the number of choices at each step or stage, and you will get the total number of final possibilities. Okay, so here it says a toy manufacturer makes a wooden toy in 3 parts, part 1, part 2, and part 3. The top part can be red, white, blue, or pink. The middle part can be orange, purple, or black, and the bottom part may be yellow or green. How many different color toys can there be using 1, a tree diagram, okay, which is what they gave us at the top of this page, and then using the fundamental counting principle. So if I use the tree diagram, okay, I take a look at part 1, which I'll do in black. So the original one starts like this, right? There's red, okay, there's the first option, then white, I have blue, and then I have pink. Okay, so there's kind of step 1 in the process, or part 1. Part 2 in blue is for now each of those first 4 original choices, I now have 3 to pick from. Okay, so I can have 3 choices now for each of those original choices depending on what I selected. Okay, so for each of those I can have orange, purple, or black. Okay, so I'll just do that: orange, purple, or black, orange, purple, black, orange, purple, and black. And then finally, part 3, which will be done in red, now can be yellow or green. So for each of these choices now, there will be 2 offshoot choices as well, okay? So what I'll do is fill out 2 possibilities for each of these, okay, and then go through to the best of my ability and go Y and G, Y, and G. Okay, obviously representing yellow and green. Okay. Oops, yellow, green, yellow, green. Okay, tough to keep track of everything in these tight quarters, okay? So now it says I count up all of those possibilities and figure out how many I have, okay? So when you count up all of those, you will see that there are 24, okay, total final results there. Now, when I use the fundamental counting principle, again, there was part 1 in making this toy, there was part 2, and there was part 3, okay? 3 stages. Okay, part 1, there was red, white, blue, or pink. That was 4 choices. Part 2 was orange, purple, or black. That's 3 choices. And part 3 was yellow, green. So that's 3. So again, remember when we were calculating to say I would make a selection for part 1, and then I would select my option for part 2, and then I would select the options that I have, or the option I have from part 3, which there are 2 choices. So multiply 4 times 3, which is 12, and 12 times 2 also results in 24. Okay, same exact final result, 2 different ways of doing it. Okay, and you're going to see we use the fundamental counting principle quite a bit more than we do tree diagrams moving forward. In the previous example, the toy consisted of part 1 and part 2 and part 3. So as I mentioned, okay, when we are dealing with that word and, okay, we are going to multiply. Okay, and again, same thing resulting here, and means multiply. Okay, that's what we want to do. And on the side, if you want to add it in, like I mentioned on the first page, okay, we'll do this. And equals multiply or equals add. Okay, so when you are hearing those phrases or you discuss them, those are the things that you're going to be doing. Next question. A Math 30 quiz consists of 8 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many sets of answers are possible? Well, again, you think about it like this. If you set up like the fundamental counting principle, what we do a lot of times is we write out blanks or spaces that need to be filled in with the options or choices we have at each stage along the way. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 blanks there, each of those blanks representing one of the 8 questions on the test. Now, for question 1, I have 4 choices, A, B, C, or D. For question 2, I have 4 choices, A, B, C, or D. Question 3, I have 4 choices, okay, and so on and so forth right to the end. For every single of those 8 questions, I have 4 choices, right? And again, if you think about what you said, you would say I would do question 1, and then I do question 2, and then, okay, and, right? And the whole way through. So I multiply 4 by itself 8 times, which would be equivalent to 4 to the exponent of 8, wouldn't it? Now, the reason I bring that up is because sometimes questions you will see don't ask for the final answer. They ask for what would the calculation look like to achieve the final answer. So they'll give you 4 possible ways of calculating the final answer, not necessarily the final calculation itself, okay? So on my calculator, when I do go 4 to the exponent of 8, okay, I do get 65,536. And those are the different sets of answers possible just on an 8-question multiple choice test. Now, fundamental counting principle involving restrictions. The most important thing here, okay, is obviously what is bolded, but you deal with the restrictions first, okay? So whatever they say in the question has to or cannot happen, you deal with that first, and then you deal with the remaining spaces or blanks in the question that need to be filled in. So let's take a look at what that looks like. Eric has been assigned the task of determining how many odd, okay, so that's important, 4-digit numbers, okay, there are. He's been told that a number like 5,267 is a 4-digit number, whereas 0267 is classified as a 3-digit number. So what you learn there is that your number cannot start with 0, okay? So there's kind of a restriction in itself that we need to adhere to when we do this final solution. Now it says the first step of his work is explain his reasoning for the number 5. So the first thing I notice is that they have 4 blanks that are drawn out here, okay? There's 1, 2, 3, and 4. Again, those represent the 4 digits of my 4-digit number. Now, the reason he has the 5 here at the end is not because that's the number 5. Remember, that's the number of options that I have for that space. Now, why do I have 5 options there? Well, because the number must be odd. Okay, the number has to be odd. That means it must end in a 1, 3, 5, 7, or 9. That is 1, 2, 3, 4, 5 possibilities. So that's why I have the number 5 there, because there are 5 choices or 5 possibilities that that number can end in. Moving on to the second part, it says the second step of his work is shown. Explain his reasoning for the number 9. Well, why do I have 9 here? Well, that again means I have 9 choices or 9 options that I can have there. Now, when we talk about digits, there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 options. But I can't use 0. That was clearly stated in the beginning of the question. So I have 9 choices. I could have a 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay? 9 choices that could be the first digit of my 4-digit number. So the last part just says complete his work now to determine how many 4 odd digit numbers there are. So again, there's digit 1, digit 2, digit 3, and digit 4. Okay, we've determined that there are 5 choices that it can end in, 1, 3, 5, 7, 9. There are 9 choices that the number can begin with, so any digit except 0, and then the 2 middle ones can be any number, right? So 10 choices, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 for both of those 2 middle blanks. So now I just multiply those values together, and that will give you 4,500. Okay, so hopefully that logic made sense and why I put the number of choices I had at each step along the way here in that process. Now in part B, it says Eric has now been assigned the task of determining how many odd 4-digit numbers there are which have no repeating digits. So here's another restriction that we have to adhere to. Part A was a 4-digit odd number, but they said nothing about repeating digits. So even if I used a 3, I could use a 3 again. This time they're saying once I use a number, I cannot use it again. So now it says explain why the first step in A is valid, but the second step is not. So here's what happens, right? I write out my 4 blanks, okay, or 4 spaces. There are still 5 options that I can have here because the number still has to be odd, okay? Number still has to be odd. Okay, so again, that means I have the potential for using a 1, a 3, a 5, a 7, or a 9. Okay, so that does not change. What changes is this first number or the number of options I have for the first blank. Okay, so what happens now is this will be an 8. It will no longer be a 9. Now, why will there be 8 choices and not 9? Well, remember, I cannot use 0. Okay, so I can't use 0. That would take it down to 9 options from 10 digits. And this time, I cannot use whatever number I ended with. Okay, so whatever number this ends in, whether it is a 1, 3, 5, 7, or 9, I don't care what it is, I can't use that number to start with, and I can't use 0. So that means there's 8 options there. Okay, so that's why the first step was okay, ending in a 5, but I have 8 options now for that first blank, not 9. So the question now just flat out asks me how many odd 4-digit numbers there are. So again, I would have 5 options to end in, a 1, 3, 5, 7, or 9. I have 8 options that I could potentially start with. I can't use 0 and I can't use whatever number I ended with. Now, this blank is also an 8. Why? Well, because I can't use whatever number I ended in. I can't use whatever number I started with, but now I can use 0 again. So now there's 8 options, and then I lose 1 option, so that's down to 7. Okay? So now I multiply these values together, 8 times 8 times 7 times 5. Okay, so that would be 2,240. Okay, moving on. Car number plates in an African country consist of a letter other than I or O followed by 3 digits, the first of which cannot be 0, followed by any 2 letters which are not repeated. How many different car number plates can be produced? So again, first thing I want to figure out is how many steps or things I have to fill in here in terms of using the fundamental counting principle. So it says car plates in an African country consist of 1 letter other than I or O followed by 3 digits. So there are the 3 digits, followed by any 2 letters. Okay, so now I know how many steps there are in the process or how many blanks I have to fill in. So the first thing says I cannot use the letters I or O. So there are 26 letters in the alphabet. I remove the I or O, that takes me down to 24. Okay, then I'm going to have 3 digits, the first of which can't be 0. So there are 10 digits. I can't use 0 for the first one. But then the other 2 I can, so it's 10 and 10 are my options there for those digits. Now, what's important here is comma, followed by any two letters which are not repeated. So this is going to be 26 and 25. A lot of people think that it goes back to the beginning of the question, where I can also not use the letter that I used at the beginning, but because of that comma, it's then followed by any two letters which are not repeated. So that refers to strictly those last two places in the calculation. So all I do now, multiply all those values together, okay? Okay, and you will get 14,040,000 as the final calculation there. Okay. Now, there are 2 routes from Pitland to Queensville, 3 routes from Queensville to St. Luke's, 3 routes from Pitland to Rutherford, and 1 route from Rutherford to St. Luke's. Okay, so obviously all those towns or cities are represented by the letter that they begin with P, Q, S, and R. Okay, so how many routes are there from Pitland to St. Luke's passing through Queensville? So here's what happens, right? I want to go from Pitland to St. Luke's, but I have to go through Queensville. So you can see here that it's kind of a 2-step process, right? Step 1 is going from Pitland to Queensville. Step 2 is going from Queensville to St. Luke's. So when I go from Pitland to Queensville, okay, there are 2 roads that I can take. And then I have 3 choices going from Queensville to St. Luke's. So that's a total of 6 roads that I could take. Okay. The second part says how many routes are there from Pitland to St. Luke's, but you have to go through Rutherford. So this time again, it's a 2-step process. Okay. The first step is going from Pitland to Rutherford, which there are 3 roads, and then there is only 1 choice. Okay, from Rutherford to St. Luke's, so 3 times 1, that's 3. So the last question says, how many routes are there from Pitland to St. Luke's? Well, you would go from Pitland to St. Luke's, you could go through Queensville, or you can go through Rutherford. Now, or means we add, right? So when I go through Queensville, that was the first calculation, there were 6 roads. Or I can go through Rutherford, which there were 3 roads, or 3 routes. So that is a total of 9, okay? But it's that or. And again, that's kind of what the notes take a look at here. So when I use or, we add, okay? And again, that's what we're focusing on here. And we had notes on that on the previous page. Now, the telephone numbers allocated to subscribers in a rural area consist of one of the following. Excuse me. The digits 3, 4, 5, followed by any 3 further digits, or the digit 2 followed by one of the digits 1 to 5 followed by any 3 further digits. Okay, so what you can see here right away is that they have used the word or. So I have 2 scenarios, and obviously I'm going to add them, okay, because of the or. So when I deal with that first scenario, they're telling you it starts with the number 3, 4, 5. That does not play into the calculation at all. Every number is going to start with 3, 4, 5. But then it's followed by any 3 further digits. So any 3 further digits, that's what I have to figure out. So if it's any 3 further digits, it's 10, 10, and 10. Okay. For the second scenario, it's the digit 2 and then followed by one of the digits 1 to 5. That's 5 options. And then followed by any 3 further digits. So that's 10, 10, and 10. So the numbers that these things start with do not affect the calculation because every number is going to start with either a 3, 4, 5, or a 2. So it doesn't matter. So what I do is I calculate these 2 scenarios. This will be 1,000. Okay. The second scenario is 5,000. And because it can be one scenario or the other, I just add them together, don't I? And that gives me a total of 6,000 possibilities. Okay. All right, last page here. Consider class example 3 in which Eric was asked to determine how many odd 4-digit numbers there are. As an extension to his assignment, Eric has been asked to determine how many even 4-digit numbers there are, and then how many even 4-digit numbers have no repeated digits. Okay, so let's work on I first. Determine the answer to I. So I just want to know how many even, okay, 4-digit numbers there are. So 4-digit number, okay, means there are 4 spaces that I have to fill in. It has to be even, right? So when it's even, there are going to be 5 choices, right? Because it can end in 0, 2, 4, 6, okay, or 8. Okay, so there are 5 choices there. Now, there are 9 choices that I can start with because it can start with any digit, but it can't start with 0. And then the 2 middle choices, there would be 10 for each of those. Okay, so again, 9 times 10 times 10 times 5, that will also be 4,500 total choices. So that one's pretty straightforward. Okay, the tricky one is this second one, okay, where it says how many even 4-digit numbers there are with no repeating digits. So this one is really, really tricky, okay, in terms of figuring it out. So it says Eric started an answer to 2, okay, which was the even 4-digit number with no repeating digits, but he was unsure how to fill in the first space. Explain why he needs to consider 2 separate cases to solve the problem. So the way he has to do this is the following, okay, there are 5 choices that the number can end in, 0, 2, 4, 6, 8. But the way I go about calculating how many choices there are for the first digit depends on whether or not my number ends in 0. Because if I use 0 to end my number in, then I'd have 9 choices, okay, to start my number with. If I don't end in 0, so I end in 2, 4, 6, or 8, then I have 8 choices to start with because I can't repeat whatever number I end in, and I also can't start with 0. So I have to basically, and I'll write it here, I have to consider 2 cases, okay? Case 1, my number ends in 0, okay? And case 2 is it does not end in 0. Okay, so there are my 2 options. So here's what it looks like, okay, when I do that calculation. So we'll just label it on the side here. Okay, ends in 0, doesn't end in 0. Okay, so in either case, we're going to have 4-digit numbers, okay, that we are trying to calculate. Okay, so if my number ends in 0, there's only one option at the end. I'm making it end in 0, there's one option. Now, I'll have 9 choices to start my number with. Because I used 0 at the end, I have 9 other options, and then I'll have 8 choices and 7 choices. Okay, so that one's pretty straightforward. 9 times 8 times 7 times 1, okay, that's 504. Now, if my number doesn't end in 0, I have 4 choices. That's a 2, a 4, a 6, or 8. That's 4 choices. Now, I can't use that number to start my number with, and I also can't use 0, so that means there's 8 options there. Okay, so now I've used up 2 numbers in total, 2 digits. So now I have 8 choices here, 7 choices here. So that leaves me with 8 times 8 times 7 times 4, 1,792. Now, remember, my number can end in 0 or doesn't end in 0, right? So or means I add. So I take these 2 values and I add them to get the total here, which is 2,296. Okay, so with even numbers, when we're talking about ending in even numbers, it really matters whether we can reuse digits, okay, or cannot use them. Okay, that really affects how we go about calculating our total answer. If you are talking about ending in 0, okay, that throws another wrench in the plans, okay, and you're going to have to probably calculate 2 scenarios and add them together. All right, last question for today. Consider the number of distinguishable, which just means different, 4-letter arrangements that can be formed from the word English. Note there's an implication that each of the words or letters in the word English only occurs once and cannot be repeated. So with questions like this, it's kind of like having tiles in a Scrabble bag. So once you've pulled it out and used it, okay, it's gone. You're not using it again. So determine the number of distinguishable, remember different, 4-letter arrangements that can be formed from the word English. So the first thing that I noticed is that they want 4-letter arrangements, but there's 1, 2, 3, 4, 5, 6. There are 7 letters. Okay, 7 letters in the word English. That's important because I'm only trying to make 4-letter arrangements. So here's me setting up the 4-letter arrangements, just like a 4-digit number. There's 4 spaces or blanks that need to be filled in. I throw those 7 letters in a bag. When I put my hand in there to pull out the first letter, there are 7 options. I use one of those. Now I have 6 options. I use one of those. Now I have 5 options. I use one of those. Now I have 4 options. So the total number of ways of making a 4-letter distinguishable arrangement from the letters in the word English when any letter can be in any position is 7 times 6 times 5 times 4. That's 840. Okay. Now, here come the restrictions. In B, they're saying E has to be first. So what do? I put E first. You can just write the letter E there. Or, because there's only one E in the word English, I could put the number 1 there to represent the 1E. So I do that. What happens? Well, I've taken the E out. I've put it first. It's always going to be first. So that means there would be just 6 options, and then 5 options, and then 4 options to fill in those 3 remaining spaces. 6 times 5 is 30 times 4. That's 120. Next one. The first and last letters must be vowels. So hopefully you guys remember what vowels are. A, E, I, O, U. Okay. So what happens is I fill those spaces in first. The first letter has to be a vowel. Well, there's 2 vowels, so I have 2 choices. Then I've used one of those vowels, so there's only 1 option at the end. And I could switch that 1 and that 2 because remember, all these values I'm just multiplying. It doesn't matter. So I have 2 options for the first space, which has to be a vowel. I have 1 option for the last space, which also has to be a vowel. There's the restriction. Now I deal with what remains. I've taken out those 2 vowels, so that means there's only 5 letters left to choose from for that space, and then 4 letters left from to choose for that space. Okay, multiply those together, and you get 40. All right, lastly, 4-letter word, it has to contain a G. Okay, so here's the thing. They don't tell you where the G has to be. So there's basically 4 scenarios here because that G could be in one of the 4 spaces. But you'll see it's the same calculation 4 times. So the G could be here, it could be here, it could be here, it could be here. Now, if I'm setting up those scenarios, it would say, I would be saying or, right? I would say the G could be first, or the G could be second, or the G could be third, or the G could be fourth. So each of these calculations, individually, I would find the value and then add them together. So let's just deal with the first one. So the G goes first. I've taken that out. So then there are 6 options, 5 options, 4 options. Okay, the second scenario, I'd have 6 options, 5 options, 4 options, 6 options, 5 options, 4 options. Okay, and again, 6, 5, 4. It doesn't matter where I place that G. I have 6, then 5, and then 4 choices for each of those scenarios. Now, each of these will be 6 times 5 times 4, which is 120. Okay, so it's 120 for each of these calculations. And I said or, right? The G could be first, or it could be second, or it could be third, or it could be fourth. So I add those all together, and you get a total of 480. Now, if you wanted to be quicker with that calculation, you could have just taken the very first one and multiplied it by 4 if you understood the way that it works. If not, then the way I did it and showed you there in the notes is obviously fine, okay? The same solution, doesn't matter how you go about doing it. All right, so that's your first lesson in permutations and combinations, the fundamental counting principle. Any questions, you guys, email and I'll get back to you.